All right, class, we're going to do section 2.4 now on continuity. Continuity is a really important principle in calculus. And I'm going to first start by giving a little bit of an intuitive definition using pictures and whatnot, and then we're going to go into a formal definition. So it says the function f of x is continuous at a point A if and only if the following three conditions are satisfied. So in our context in Calc 1, this is going to be the way we look at continuity. First of all, the function has to be defined at the point we're looking at. Second of all, the limit has to exist as x approaches a at that point on the graph or on the function. And the last verification is that the two things we just found, the value of the function and the limit, have to both agree and have to be equal. Otherwise, it says a function is discontinuous at a point A if it fails to be continuous at A. So if any one of those three fails, okay, so if any one of these three fail, then we have discontinuity. Okay, so let's take a look at some examples here. Let's look at example number 1 here. Well, it looks like this example right here is going to fail. And the reason it's going to fail is because of number 1 up above. The function is not defined at A. It actually has a hole at A. So this is discontinuous, all right? Because it's not even defined, so we can't even get to step 2 to see if the limit exists. It does turn out the limit does exist, just to verify, because if I take the limit as x approaches from the left and right of that point, I do get a limit right here of that height, whatever that is. So the limit does exist, but the function isn't defined, so this is not continuous. Okay, the next one. It looks like the limit does exist. If I go from the left and the right, my limit is right here, whatever L is. But up here is the value of the function. This is my value of my function. Is up at that height where the dot is. So first of all, f of a is defined, and it's that dot up above. The limit as x approaches a of f of x does exist, and it's that L down below. But the problem is that the value of the limit and the value of the function do not agree. So that is not a continuous function at that point A. All right, so the first two are satisfied, the third one is not. We call that a removable discontinuity. We'll explain what that means later, but essentially what a removable discontinuity is any continuity where if I just change the definition of a function at one point, I can fix the discontinuity. So if I just literally just said right now, I'm just going to change the definition at A to this instead, I just had to basically change the definition of the value of the function at that one point to fix this discontinuity. Okay, so that's removable. That's what it means to be removable. Second, we call it a jump discontinuity. Well, f of a is defined. Okay, f of a is right here. Here's my f of a. The dot, the solid dot is the f of a. The problem is, so f of a is defined up above. Does the limit as x approaches a of f of x exist? No, it does not. Because the limit doesn't exist because the left and the right-hand limits do not agree. So since the limit doesn't exist, this is not continuous, even though it is defined. So all you need to find is one of those three things that doesn't satisfy it, and you know we have a discontinuous. So you can just kind of run through them each individually. Okay? All right. Now, the last one, we call this an infinite discontinuity because actually nothing is satisfied in this example. Because if you look, f of a is not defined because at a we have an asymptote, which means that there's no value for the function. The limit doesn't exist because it's an infinite limit on the left and the right, and therefore it doesn't exist. And even if they both went to infinity, if it looked like this and it went to infinity and left and the right, that still is not an existing limit. It's just a more descriptive way of saying how it doesn't exist by saying it goes to infinity. Okay, we've talked about that. And so therefore, since 1 and 2 are not satisfied, neither can part 3 be satisfied, because there's no hope of them being equal if neither of them exist or are defined. Okay, so that's continuous at a point in an intuitive way. Okay, let's scroll down here a little bit. So what's our strategy for determining if something is continuous? Well, we just kind of went through it. We first check to see if the function is defined. If it's undefined, we go no further. If it's not defined, we have no hope of the value of the function equaling the value of the limit, because the value of the function doesn't even exist. It's undefined. Next, we compute the limit as x approaches a. We need to make sure we check both from the left and the right to make sure we have agreement. And if the limit doesn't exist, then we don't have to go any further. The function is not continuous at a, and the problem is solved. If we discover that the value of the function is defined and that the limit does exist, we need to make sure that the value of the function and the value of the limit are equal. The things we found in parts 1 and 2 are equal. If they're not equal, it's not continuous. So let's take a very, very simple example here, about as simple as we can get with continuity. Using the definition, determine whether the function f of x equals x squared minus 4 over x minus 2 is continuous at x equals 2. All right, so let me get this back to black, sorry. I'm going to rewrite this here. All right. Is that continuous at x equals 2? Well, it looks to me that this is not continuous at x equals 2. And why is it not continuous? Because if I stick in 2 for the denominator, I'm dividing by 0. If I stick 2 in the denominator. So that implies that that f of a, or f of 2, is undefined. F of 2 is undefined. And if the value, if the evaluation of the function at 2 is an undefined quantity, then we certainly do not have continuity. If you remember from your pre-calc days, I'm not going to go super in-depth with this, that I could actually simplify this algebraically, this expression. I could factor this, x plus 2 times x minus 2 over x minus 2, and notice that the x minus 2's cancel. So this function is actually algebraically equivalent to x plus 2, which basically means that what this graph will actually look like is if I graph the line x plus 2, it actually has a y-intercept of 2 and a slope of 1. That's roughly what my graph looks like. That's the picture of the line y equals x plus 2. So the only difference between the line y equals x plus 2 and this function, which are algebraically equivalent, is that the function up above, the original function, is going to have a hole where the denominator is 0, which would be at x equals 2. So basically, that graph f of x is this picture I have right here with a hole up here at x equals 2. That's a hole. So this is actually f right here. That picture. If you remember pre-calc days, that's how we handle when we have a factor that cancels. Essentially, the graph looks like the graph after the cancellation, the function after the cancellation, except that we have a hole wherever the denominator was 0 in that canceled factor, caused by that canceled factor. So this is the graph. So this is actually going to be a removable discontinuity, because all I'd have to do to fix this discontinuity is change the definition of the function at this point right here. And remember, I said a removable discontinuity is a discontinuity where all I need, if I could change the value of the function at a given point and get rid of the discontinuity, then we call it removable. Okay, so that one's pretty simple. Function's not even defined. Let's take it the next one. The condition 2 is going to be violated here, but let's discover how. So first of all, let's look at condition 1. Let's look at the value of the function at 3. We're checking if this function is continuous at 3. Well, it looks like the value of the function at 3 is just going to use the top definition, because it says that f of x equals negative x squared plus 4 if x is less than or equal to 3. So this is equal to 3. So it's going to be negative 3 squared plus 4, which is negative 9 plus 4, which is negative 5. So yes, criteria 1 is met. This function is defined at 3. Okay? Now let's check the limits. And in order to check condition 2, we're going to check the limit as x approaches 3 from the left of f of x first. In order to do that, we're going to use the top definition, because that's when x is less than or equal to 3, we are to the left of 3 on the number line. And since it's a polynomial, I'm just going to do direct substitution. So that'd be negative of 3 squared plus 4, which is negative 9 plus 4, which is negative 5. All right. And the limit as x approaches 3 from the right of f of x, plugging in 3 in the other side, that's 12 minus 8, which is 4. Okay. These do not agree. They are not equal. Therefore, the function is not continuous. Since the limit as x approaches 3 in general of f of x does not exist. Sorry for the noise, guys. Someone's doing some crazy excavating next to my house. So if you can slightly hear that grinding. All right, so this is a situation where condition 2 of the criteria above was not met. Let's move forward. Here's where condition 3 is not met. So this is kind of a weird one. Using the definition to determine whether the function f of x equals sine x over x if x is non-zero, and 1 if x is 0. So basically this function is defined to be a horizontal line everywhere. It's not a horizontal line, sorry. This function is defined to be sine x over x when x is non-zero, and it's defined to be 1 if x is 0. So we're trying to find out if there's a jump here or what's going on. So let's look at this. So let's look at criteria 1 first. Well, we're checking at x equals 0. So f of 0 does have a value, and it's 1. So yes, this function is defined at x equals 0. They tell us the definition right there. Okay, so criteria 1 is met. Criteria 2. Well, if we take the limit as x approaches 0 from the left of f of x, that's just going to be the limit as x approaches 0. Sorry, my bad. Yeah, that's right. Of sine x over x, because what's interesting about this problem is from the left and the right, we're going to use sine x over x, because this function is actually equal to sine x over x on both the left and the right side of 0, because the only place it doesn't equal sine x over x is literally at 0. So this is one of those special limits I talked about in the last lecture. We just should know this is equal to 1. Okay? The limit as x approaches 0 of sine x over x is 1. I mentioned that in the last lecture. That's one of the special ones we should just know. And then let's take the limit as x approaches 0 from the right of f of x, which will also be the limit as x approaches 0 of sine x over x, because we're using the value of the function on the right side of 0, which is also sine x over x, and that also equals 1. Okay. And so it appears that the limit as x approaches 0 in general of f of x, of this piecewise function, is equal to 1, because these two agree. If the left and the right hand limits are equal. All right, so now, does the value of the function, checking criteria 3, it appears that the limit as x goes to 0 of f of x is equal to 1, but it also appears that that's the same as the value of the function. That was criteria 3. If the value of the limit as I approach 0 is the same as the value of the function at 0, then this is a continuous function. So therefore, continuous since the limit as x approaches 0 of f of x is the same as f of 0. Okay, check. So basically, we did an example kind of each where, this is the first one where condition 1 was violated because this function is not even defined at the spot we're looking. Here, condition 2 was violated because our left and right hand limits were not equal. Therefore, the overall limit didn't exist, which means it cannot be continuous. This is a jump in the graph. So this first one was a removable discontinuity because it just had one point that was a problem. This is a jump discontinuity because from the left we were going to -5 and from the right we were going to 4, so there's clearly a jump there in the graph. And then this last one actually ended up being continuous. Okay. Now, polynomial and rational functions are continuous at every point in their domains. So what that means, guys, we've already kind of discussed this in the last section, but that means that I'm dealing with a polynomial or a rational expression. If I'm trying to evaluate a limit, I can just do direct substitution because since this is continuous, we know if I call that f of x, then I know that the limit as x approaches -2 of f of x is just going to be f at -2 because we know it's continuous. And the definition of continuity says that the value of the limit at a point is equal to the value of the function at that point. So that means I can literally, to find the limit, I can just plug in -2 for x. I can just plug in -2 into the function. So that'd be 3 times -2 cubed minus 7 times -2 minus 11. We already knew this from the last section, that with polynomials and rational expressions, if we want to find the limit, we can just do direct substitution. This just confirms that idea with continuity. So this would be 3 times -8, which is -24, plus 14 minus 11. -24 plus 14 is -10 minus 11 is -21. Okay. Same thing here. The only glitch with rational functions is it says that polynomials and rational functions are continuous at every point in their domains. So remember that anytime the denominator is 0 for a rational function, that value is not part of the domain. So the only time we're going to run into a problem with direct substitution when we're performing a limit on a rational expression is when the value that we're direct substituting gives us a 0 denominator. So let's see if that happens in this case. If I plug in 2, this should be 4 times 2 minus 13 over 2 cubed minus 4 times 2 plus 2. So what do I get there? I get 8 minus 13 is -5. And then I get 8 minus 8, which is 0, plus 2 is 2. So it turns out I do not get a 0 denominator problem. So this theorem up above holds in this particular case. All right, let's keep moving. So we already talked about this, just reiterating. F has a removable discontinuity. If F is discontinuous at A, then F has a removable discontinuity at A if the limit exists. Okay, so if we basically go to test the continuity of something and we discover that the only problem is that criteria number 2 is violated. So let's say criteria 1, the limit or the value of the function is defined, but criteria 2, let's say that criteria 2 is that the limit exists. That means from the left and the right, we're coming to the same number. All right, same height. Then that's a removable discontinuity. So probably what happened in case 1 is that we either had a situation like this with a hole, or we had a situation like this where there's a jump. Okay, that's a removable discontinuity. Is either the hole or the jump. It's not really the jump in the graph, but just we have a hole where the value is defined above or below it. Okay, those removable discontinuities look like. A jump continuity is when the limits from the right and the left both exist, but they don't agree. Okay, that's this situation, right? That's this kind of situation, right? Or something similar to that. And then an infinite discontinuity is obviously when we have an asymptote, right? And there can be lots of different variations on that theme. We can have them both going to infinity, both going to negative infinity, one going to infinity, one going to negative infinity, and on either side, respectively. So that's kind of the difference between the removal discontinuity, the jump discontinuity, and the infinite discontinuity. But the algebra, pay attention to how you identify it without a picture. Removal discontinuity, the limit exists. And as you can see here, in both of these cases, the limit does exist when we go from the left and the right. They're both approaching the same height, even though the value of the function is different in that one. In the second case, the limits are not the same from the left and the right. And in the last case, the limits are infinite as we come from the left and or the right. So let's take a look at this one. For f of x equaling x squared if x is not equal to 1, and 3 if x equal to 1, determine whether f is continuous 1. If f is not continuous 1, classify the discontinuity as removable, jump, or infinite. Okay, so let's try that. So let's try criteria 1. Let's first evaluate the function at 1. Well, it does have a value right here. It tells us it does, 3. So criteria 1 is met. Let's do criteria 2. We're going to take the limit as x approaches 1 from the left of f of x, which, since x squared is the definition of the function on both the left and the right-hand side of 1, because the only time that it's not equal to x squared is when we're right at 1, where the value is 3, then this is going to be the limit as x approaches 1 of x squared, which I can do direct substitution. That's just a polynomial, which is 1. But that's also the same limit from the right, isn't it? Because it's the same procedure as the right. So the left and right hand limits are equal, okay, and they both equal 1. All right, so I'm going to underline what these equal. So the value of the function is 3. The value of the limit from the left and the right is 1. So that implies that the value of the limit in general, since the value of the left and right hand limits are the same, is 1. Right? But notice what happens. Criteria 3, the limit as x approaches 1 of the function, which is 1, is definitely not equal to f of 1, which equals 3. Right? So this, the value of the limit, is not equal to the value of the function. So 1 and 2 criteria are not equal. So this is discontinuous. And what kind of discontinuity is it? It's a great question. Well, remember we said that if the value of the left and the right hand limits, the value of the left hand limit and the right hand limit are both the same, which they are, they're both equal to 1, the limit does exist, then that would be a removable discontinuity. So once we determine that it's discontinuous and we discover that the criteria 2 is met, that the limit exists, then we probably have one of these two pictures when we graph it. That means we have either a hole or a hole with a definition of the function above or below. So this is a removable discontinuity because the limit exists. It is discontinuous because criteria 3 is not met. So we would call this a removable discontinuity. because, and it's always good to explain ourselves, because criteria 3 fails and the limit as x approaches 1 of f of x exists. Okay? That would be my explanation. That's the logical explanation. I explained why it was discontinuous because criteria 3 failed, and I explained why it was a removable discontinuity because the limit exists. And I'm using this idea right here in the definition. Okay? Now, continuity from the right and left is a common idea as well. Not super hard to understand, very similar to something being continuous from right and left with an extra added detail. So let's take a look here at something. So if I draw a picture, I'm going to just create some pictures here and we'll talk through them. If I create a picture like this with a little dot, and then I go like that. Okay, let's say I have a jump. Looks like a jump discontinuity. It is a jump discontinuity. And if down here is my A, this is A, x equal A. All right. So it looks like if I want to check continuous from the left, I want to check if the limit as x approaches A from the left, my bad. Limit as x approaches A from the left of f of x is equal to f of A. So let's check that. So let's first do the limit as x approaches A from the left of f of x. Well, it looks like the limit as x approaches A from the left is whatever this height is. Well, what is that height? Well, it looks like that height is actually f of A, isn't it? Do you guys see that? Because that's a solid dot right there, so that's the actual value of the function there. So it looks like it is f of A. So that is continuous from the left. Let's check if it's continuous from the right. Limit is, if I take the limit from the right now of the function, what does that equal? Well, if I take the limit from the right, it's approaching some height up here, which is, I don't know, just call it some L. And that L is not equal to f of A. Okay? Because f of A is down here in green. So this is continuous from the left. But not continuous from the right. Okay? Now we can alter this a little bit and make this a little bit more complex. But essentially, the only thing I could do to make this a little bit more complex is to change where my solid dot was, right? So the intuition of this is, guys, this is continuous from the left because the dot is, the left-hand curve comes into the solid dot, whereas the right-hand curve comes into the open dot. If I just switch the dots to make this one solid and this one open, this would be continuous from the right and not the left. So that's just kind of how we tell continuity from the right and left. Obviously, if I gave you a piecewise function, you could look at this in formula form as well. So I could alter this just a tad, and I'll just draw that, what I just described, is if I did something like this. We're not going to rigorously do this. I should have erased that, my bad. I'm going to erase that. And then I'm going to do an open hole there, have a jump discontinuity and go there. All right. And I'm going to call this A, and I'm going to call this one B for the x values, and I'm actually going to throw a jump in the graph right there, a little definition there. So that's my function f, and you can tell here, just looking at this intuitively now, it looks like at f that I have continuity from the right because I'm running into the solid dot, but I do not have continuity from the left because I'm running into the open dot. So the value of the limit on the right, from the right, is going to equal the value of the function, because the value of the function is right here. That's f of a, f of b, my bad. So that's my f of b, and it looks like the value of the limit is also f of b at the same height. But coming from the left, I don't have that luxury because my f of b is chilling out up here. But my limit as x approaches b from the left is some other height that I could call L. So that one is continuous from the right and not the left at B. Now at A, it's neither continuous from the right or the left, because in both cases, right and left, my limit is L, but my value of my function, f of a, is up there. So this is not continuous from the right or the left. And as you might imagine, the only way a function can actually be continuous in general is if it's continuous from both the right and the left. If a function is continuous both from the right and the left, then it is continuous in general at that point. All right, let's move on to the next idea. Continuity on an interval. So now that we've talked a little about continuity at a point, let's try to determine where a function may not be continuous on an entire interval. So state the interval over which the function f of x equals x minus 1 over the quantity x squared plus 2x is continuous. Well, we've already talked about how rational functions are continuous everywhere on their domain. So all they've got to do is find places where the denominator is going to be 0, because that would be the only, where the denominator is 0 in this rational function is those are the only places where this function is undefined, and therefore the only places where it would be discontinuous because of the theorem we had previously. So if I rewrite this as f of x equals x minus 1, and I factor the bottom to x times x plus 2, I notice that x is not allowed to be 0 or negative 2 in the domain of this rational function. So that means that this function is continuous if I draw a number line. Just to do it with interval notation, if I stick those on the number line, f of x will be continuous with an open hole going that way, an open hole going to an open hole that way, and then an open hole going that way. Okay, and so there's 3 intervals there that where the function is continuous, and notice I put open holes around -2 and around 0 because I don't want to include those. So the way I write those intervals is the first interval is -∞ to -2 with parentheses around both. The second interval is -2 to 0 with parentheses, and the third interval is 0 to infinity. And then when I have 3 intervals that I want to team up with each other to make a larger interval, I just put the little union symbol between them. Okay? You could also write it in words, all reals except for x equaling -2 and 0. Okay? That's another way to say it. You could say it in words. Okay. But that's how you write it in intervals. That's a review of pre-calc as well, if you remember that. So since that's a rational expression, we can just eliminate things that are making the denominator 0. Now, here's a little bit more tricky one. State the interval over which the function f of x equals the square root of x plus 3 is continuous. Well, this one's a little bit more challenging, but not much more challenging. The only time we're going to run into a problem with this is when we have a negative under the square root. We don't want to have negatives under the square root because in the real number land we can't take negatives. We can't take square roots of negative numbers, and we want to stay in real number land. We're not doing imaginary numbers in this class. So I want x plus 3 to be bigger than or equal to 0 is what I want. So I want this to be true. Okay, well that implies that x is bigger than or equal to negative 3. The way I write that as an interval is I make a bracket and I do negative 3 to infinity. So that is the interval where it's continuous. A square root function would only be discontinuous in places where we have a negative under the square root. You've seen a square root function before. It is a smooth function with no jumps and with no holes. And so we're just looking for where that starts. So an intuitive definition of continuity when you're looking at a picture is that I can draw it without ever lifting my pencil. The only thing wrong with that intuitive definition is that it's hard to imagine drawing for all of eternity to the left and to the right. But other than that little breakdown in the metaphor, as long as you can draw something without ever lifting your pencil, it's a continuous function for our purposes. All right. Now, composite functions, this is a theorem. We're not going to prove it, but it basically says that f is continuous at L, and the limit as x approaches a of g of x equals L, then the limit, if f of x is continuous at L, and the limit as x approaches a of g of x equals L, then the limit as x approaches a of f of g of x is equal to f of the limit as x approaches a of g of x, which is equal to f of L. So here's what this basically says, guys, is that if you have a function inside of a function, as long as the inner function has an existing limit, okay, and the outer function is continuous at whatever that limit is, then the overall limit can be found just by plugging in L to the outer function. Okay, so here, let's do this simply. So basically what it means is this, is that the limit as x approaches pi of the sine of x minus pi, notice we have an inner function and we have an outer function. We have one function inside of another. That's what composition is. I can basically move the limit inside of the sine. So I can do this. That's what this essentially means. I can do the sine of the limit as x approaches pi of x minus pi, and then I can just ignore the outer function for a second, evaluate this limit. Well, that limit I can do by direct substitution. If I put in pi for x, I get limit of pi minus pi, which is limit. I get 0. So I just get 0 inside. That limit is 0. So that means that this will just end up becoming sine of 0, which is 0. The only glitch we could have, guys, is if inside I get a value that maybe is not a place of continuity for the outer function. So like an example would be where I'd run into a problem is if I told you to do the same thing, where I told you to do the limit as x tends to pi of the ln of x minus pi. Okay, now if I move it inside, I run into a problem because then I got to take the ln of 0, right? I got to take the ln of 0. Now, it turns out that we can sort of think about this problem and find a solution to this. We can find an answer to this. But with the theorem that we're using above, the theorem we're using above does not apply, because if you plug the natural log of 0 into your calculator, you get an error. So this limit is it's actually gonna technically equal negative infinity. But that's a longer story. So just for now, recognize that the theorem we just looked at doesn't apply to the situation right here. It doesn't apply to this situation because the limit of the inside is a spot of discontinuity for the outer function. Okay, so you won't get any problems like that in the homework. Most of your problems are going to be where you have inner and outer functions are going to be ones where you can just evaluate the limit inside, get some sort of value, and then just plug that value in. So you basically slide the limit inside, like I did here in the example. All right. Intermediate value theorem. Seems challenging, but it's actually not that challenging once you understand the picture. So if I have a continuous function over a closed bounded interval, so closed and bounded means it's an interval where I include the two endpoints, A and B in this case. So I'd include the A and I'd include the B. If Z is any real number between f of A and B and f of B, so if I have a function here, you can see my picture here of the function. So if I have some random function and I have my f of A and my f of B, and my A and B are here set, and I pick any value in this area right here between f of A and f of B, okay? I pick any value. So they just kind of arbitrarily picked one there. Then there has to be a number C in A, B satisfy. There has to be a number C in there that when I plug it through the function gets me to Z. Okay. Now, why do I need continuity? Because if you imagine, I'm going to draw a little picture over here. Whoops, I'll draw it in black. Why will this not work if I'm dealing with a discontinuity? Let's just take one example of a discontinuity. Okay, if I pick my A to be here now, so let's do everything that the theorem just says. Let's say I have an A and B. Okay, and my f of A is up here. And my f of B, sorry, that's my f of B, my bad. I screwed that up. And my f of A is down here. So similar picture, except I drew a discontinuous graph. And I pick a random Z in the middle. It says then there is, if Z is any real number between f of A and f of B. So I'm going to pick a random one in there. So I'm going to pick this Z right here. Then there is a number C in AB satisfying f of C equals Z. Well, is there any number in this region right here where if I send it through the function, it gives me Z? The answer is no. Because if you look, pretty much all these values right here map to things that are like here and down, right? And then all the values from here to here map to things that are here and up when we put them into the function. So in this little region right in here, this little region right here of Z, all those things, there's no value that maps to any of those things in this little region here between the green and the red horizontal line that I just drew. So this is why the function has to be continuous, because if it's not continuous, I can have a jump where there's a bunch of values in here that don't ever get mapped to from the original function between A and B. Okay, it's kind of complex to understand, but hopefully that helps a little bit. I'm going to erase that. Now, this is really useful because it allows us to guarantee that there's going to be a value there. And here's an application of it. So let's say I give you a function, f of a polynomial function, which we know polynomials are continuous everywhere. So let's first note that. Let's write that down. Let's note f of x is continuous everywhere because polynomials are continuous on all x's. We know that from before, okay? So we want to show that this has a 0 over the interval 0 to 1. So we're going to use the intermediate value theorem, and here's where we're going to use it. We already satisfied one of the hypotheses of the intermediate value theorem is that f has to be continuous over a closed bounded interval AB, which in this case is the interval 0 to 1. So f is continuous everywhere and on 0, 1. So we have to state that because we're trying to meet the hypothesis of the theorem so we can come to the conclusion. So now we want to see that there's a 0. So we basically want to show that f of something between 0 and 1 is going to equal 0. What it means for a function to have a 0 is it means that there's some value we can put into the function that gets us an output of 0. That's what it means for it to have a 0. So we want to show that f of c is equal to 0 when c is in the interval 0 to 1. Okay? When c is in the interval 0 to 1. How do I prove that? Well, let's first find f of 0. Let's find what f of 0 is. If I stick in 0 for f, I get 0 minus 0 minus 0 plus 1, which is 1. I think you can handle that. Put in 0 for all three of those. And what's f of 1? Well, that'd be 1 minus 3 plus 1, which is 0 minus 3, which is minus 2, plus 1 is minus 1. So f of 1 equals minus 1. Well, now we know that f of 0 is 1, and we know that f of 1 is equal to minus 1. So that means that somewhere in between, since this is continuous and we would never be able to lift our pencil, so if we create like a little picture here, if f of 0 is, f of 1 is negative 1, and f of 0 is 1, then some negative between negative 1 and 1 is 0, correct? So there has to be some c that I can put in that when I run it through the function gets me 0 because the function continues. That's what the intermediate value theorem says, because notice 1 is above 0 and negative 1 is below 0. So that means that there has to be some c that when sent through the function gets me z, which in this case is 0. So it's very simple, guys. I can't, basically, if the value of the function was negative 1 at a point and it was 1 at a point, and I have to get from negative 1 to 1, I have to connect the dots. I can't ever lift my pencil. I'm eventually going to have to cross the x-axis, which would be when the value of the function is equal to 0. That would be the x-intercept, or the 0. So therefore, since f is continuous, CTS means continuous on the interval 0, 1, and f of 0 is equal to 1, and f of 1 is equal to negative 1 by the intermediate value theorem, IVT, we can abbreviate it. F of c must be 0 for some c in the interval 0 to 1. That's what the intermediate value theorem tells us. So let's take just a miniature picture in 3D or in 2D, I guess. We don't even care at this point what this actual function looks like, But if it's 0, I'm at 1. And at f of, let's go 1, 2. And if f at 1, I'm at -1. And I know this is continuous. Doesn't matter what the shape of it is. I've somehow got to get from this point to that point without ever lifting my pencil. So at some point, I don't know, make whatever you want. Some point in there, this is my C, I've got to have a 0 to the function. So all I need to do, let's review this in a minute here. What I need to do is I need to first, to make the intermediate value theorem come into effect, I've first got to state and explain why it's continuous on the interval I'm looking in, which is the interval in this case from 0 to 1. Once I've stated that, I need to check the value of the function here and here. If one of them is above 0 and one of them is below 0, then it's guaranteed at some point the value of the function is equal to 0. And then I just sort of state that. Once I notice that one is above, I say, therefore, since f is continuous on 0, 1, and I know that one value is above 0 and one value is below 0, the intermediate value theorem guarantees to me that there's got to be somewhere that it equals 0 in that interval. So this is how you'd actually write out formally what you found after you showed your work as I have done it here. All right, hopefully that helps you with the homework. And if you have any questions, just make sure you get in touch with me and we can do a one-on-one Zoom. It's weird doing these lectures in like the context of me alone in a room with, you know, a PDF. You know, I don't always speak as clearly as I want, and I don't get to correct myself as much because I'm trying to make it as fast as possible to correct my wording. So please make sure you're setting up Zoom meetings and coming to office hours if you need it.